Okay, let me put this at the beginning. Page sorter. Okay, let me take this down. Okay, here. We are here. Okay. So, what we studied the other day was Hooke's law. We said that the force is equal to K multiplied by X. I also told you that there's a minus here that you don't use in applications. I also told you that this thing here, what is meant by the minus, I told you, is to show you that the force. Okay, how can I move this thing? Let me try this. Okay, here. So the other day we said that okay, there's no minus. That's the minus. Okay. So the other day we said, let me make this red. Okay, that's red. Okay. So this here, the X is called a displacement. X is the displacement. Also, I told you that X has another name. X is the change of length of the spring, of course, and X is the elongation or the compression. You know the difference, right? I hope that you know the difference. I'll just put compression. So if it's an elongation, the X will be more than 0. And if it's a compression, X will be less than 0. Okay, so we talked about Hooke's law. We talked about this K. K is called the force constant or spring constant or force constant or spring constant or stiffness constant. So if K is a large number, you'll know that you're dealing with a spring that is very stiff. Okay. Okay, today let's talk about something new. It's called the elastic potential energy. Every spring has its own elastic potential energy. So if you compress it or elongate it, it will store energy. And to calculate this energy, what you need to do is, what you can do is, you find half. Let me try to use the mathematical equation here. Let's see if it's helpful. Okay, that was dramatic. Let me try to write. So elastic potential energy equal half. Okay, the fraction is somewhere here. Yes. So this is exactly the same as the other one. Okay, no, not this one. So here it's a half. Okay, multiplied by, let's see if it takes brackets. Of course it does. Here we have K, and here we have X, and I should raise this to the power of 2. So I need the power, this one. Okay, you can see what happened here. I'll try to put it inside the bracket and put 2 here. Okay, that's it. Insert equation. We're inserting the equation here. That's the elastic potential energy. So what you need to know about this, you need to know that potential energy, potential elastic energy elastic potential energy, sorry, it has the unit like any energy, joules. What you need to know is X is in meters, so you have to change it to meters. You need to remember that. Actually, this applies here also. This applies here. Okay, let me check this one. This applies here. Let me do this. Okay, so we talked about Hooke's law, we talked about the elastic potential energy. Okay, so the elastic potential energy here has two limits. Sometimes it's 0 when this X is 0, and sometimes it's maximum when the X is maximum. The X is maximum if you have maximum elongation in the spring. So let me go now to the next page. Okay, I'm trying to open the next page. Hopefully it will open. Okay, page sorter. Okay, so if I take this down, no, it's not working. Okay, it's working. So what we need to write here in the next one, we need to write that if a spring is okay, you know what I'm thinking? I'm thinking how about I just yeah, do it the other one here. Yes, so I want you to think about the following idea. I want you to think about this case. Do you think the elastic potential energy in this particular case is sorry for that. So do you think the elastic potential energy here is maximum or minimum? You have till I type it. So what do you think? If you need more time, you can pause. The answer is, in this case, X, which is here the elongation, is max. Therefore, we write that elastic potential energy is maximum. Okay? Let's check the other case. So I like to copy paste here. I'm moving it to this place, and by double clicking I can edit it. Okay, so here the elongation is minimum because this is the resting place. Resting place is a bad term, yes. It's this is the location where the spring is unstressed, right? So I'll just write here minimum. I'm implying 0, and the potential energy actually is minimum. Okay. Let me write 0. Yes, 0 is very clear, and here also 0. Okay, so in the other one, like in this case, what is happening here, we have again, we still have compression, but the compression we have is what? It's in the other direction, so it's not compression. I think I made a mistake now. This is not a compression, it's an elongation, but in the other direction. Okay, so it's going in this direction. That's the elongation. No, it's a compression because the spring has lost length. So it went from here to there. It has lost length, so definitely it's compression because X is equal to L final minus L initial, so the length of the spring is becoming less. There's compression in this case. So here let's call this compression, and when the compression is maximum, the potential energy is maximum. Okay, now I want you to think about this case. What am I talking about? I'm talking about the mass spring system, and this system is oscillating back and forth in a simple harmonic motion. It's called simple harmonic motion because the F elastic is a function of the displacement. Okay, now I want you to think about the speed. What happens to the speed in this case here? In this case the speed is 0. In this case the speed is maximum. In this case the speed is also 0. So what's happening here is that this box is going forth back like this. So it stops for a moment here. It stops for a moment here, but here the speed is maximum in the middle. So if I just copy this one and type here down this one, and I choose another color, this for example, but instead of X, let me choose the speed. Let me choose V. So in this place the V is equal to 0, and instead of potential energy here I'll put kinetic energy. So people who took or who've read anything related to mechanics or maybe science from grade 9, you would know that kinetic energy is the energy related to motion, okay, which is equal to half times mass times speed square, mv square over 2, or half mv square. So in this case, as you can see in front of you, the kinetic energy is 0 because the speed here is 0. Equally, the speed here is 0, but here the speed is maximum. So let's write here. Let's write the speed here is max. So the kinetic energy is max here in the equilibrium position. We call this the equilibrium position. Okay, and in the last case here we will write we will just repeat the first one. Okay, we will choose this one, take this, we want this one, and let me go to typing and put it here. Okay, so this should be 0. That's correct here. Okay, what I want to share with you right now is in the next slide. Let me check the next one. In the next slide, this one, yeah, what I'd like to share with you is not this one. Let me remove this one. Actually I want to share something here from this one. It's from this one, from paint, I think. Yes, this thing. So if I use the annotate this capture thing, okay, what happened? Because I did it before. Let me try to do it now. Again, let me do the capture. Okay, not this one then. I think the capture should be somewhere here. Not capture, I need not freehand. Which one? not zoom, not capture, freehand, page up, page down, spotlight, no, not this one. No, it's I need to put that picture here. I don't know what I should do. Let me just copy the picture. It's a good idea. I'll copy the picture from here. Okay, that's it. So Control A, copy everything, go back to the presentation. Also a problem, let me check why. Okay, now, yeah, it's working. So what do we do here? First of all, let me put here, we have 1, 2, 3, we have 4. Let me put 4. Let me put 4. Let me duplicate 1, 2. I think this is enough. Okay, so let me go back. Not this one, not this one. Yeah, this one. Let's see the first one. So suppose the spring, so I'm solving this one right now. Suppose the spring in sample problem A, let's check the answer of sample problem A, only the answer, 330. Okay, let's go back. So let me type here before going further, let me just type that K here is equal to 330 Newton per meter. Let me give this a space, let me stop here. Okay, so suppose the spring in sample problem A is replaced with a spring that stretches 36 centimeter. So here they're telling us that X is equal to 36 centimeter, but we should not leave it in centimeter. We should divide by 100, so the answer is 0.36 meter. Or if you're using scientific mode, which is the correct thing, which is a better thing, the answer will be 3.6 times 10 to the power minus 1. But I'll accept this for the time being, considering. Okay, what do they want? They want K here. So they want another K. So K in this problem equal to question mark. Let me give it another color to celebrate. Okay, so K is equal to question mark. So how do we solve this problem? You can pause and guess, think about it for a couple of seconds, 20 seconds, the same time required to wash your hands. Okay, so let's go to this one. If you guessed it, that would be amazing. The answer here is we apply Hooke's law. So let's apply Hooke's law here, and we put F equal minus K X, and the place of the force we put we should use the force in the other one. Suppose the spring in sample problem A is replaced with another spring that stretches from the equilibrium position. Okay, let me do this. Let me try to move this. So the spring here is replaced with a spring that stretches 0.36. What is the spring constant in this case? Okay, we should go back and check the force applied, right? The force applied in this case was here, remember, it's a mass. Here it's a mass, right? Let me zoom in to make sure that you understand, you can see. Okay, so there's a mass, and the mass is not a force. So they multiplied this one by G, so they have the weight. So the weight is mg. The minus is simply because they put F not equal to 0. Never mind that. Just remember that the force is m times g. So the force that we're looking for is 2.1 multiplied by 9.81. That's the force that we want. 2.1 times 9.81. Okay? So let's go back to our problem. I forgot the force. 2.1 times 9.81. Let's continue editing here. So in the place of force, I'll put 2.1 and here 9.81. This k is equal to minus, the k is unknown, and the x is what? It's 0.36. Okay, so what I want you to do is find k, get the answer, and check if that answer is bigger than 330 or smaller. So is this spring stiffer? If your k, the answer here, is bigger than 330, you say yes, it's stiffer. If it's smaller, you say no, it's not. Okay, so I'll conclude now this problem. I'll stop the recording and I'll go back to number 2, then 3, then 4. Okay.